Hey guys, in this video I'm going to show you how to code the discrete Fourier transform. If you haven't seen my other video on the Fourier transform itself, I highly recommend you do that so you understand what exactly we're doing. To put it short in terms of audio programming, we're basically sampling cosine and sine waves, parameterized by a particular frequency, namely the bin frequency, and that will tell us how much of that frequency is present in the sample wave. That's what the discrete Fourier transform does. In that video, I think I went over a bunch of Desmos documents, and I think this was one of them. But basically, as a reiteration of what this Desmos document does, it takes this wave here, this is the sample here, and it basically does the Fourier transform on it, which I show here. So we take the Fourier transform of it, and then we do the inverse Fourier transform, and then that is shown here. So I think this should actually be a plus. Yeah, there we go. So if you don't know what this is or makes sense, I recommend you check out that other video. This is interesting because I've already done my FFT videos, but in that video I referenced this video, and that's because this was originally posted before, but I decided to redo it because my microphone quality was quite bad. But basically, what the Fourier transform is also doing is it is rotating the signal in a circle. That's another way to think about it. And what this formula really is it is a two-dimensional transformation. So I'm going to open up this. So this is the general formula that's used here. Now, this is the FFT specific version, but the idea is we are using this rotation formula of x times cosine and y times sine. However, in the Fourier transform, x and y are the same. So you get x and y, they're actually both that way. So if we take a look at this and sort of see how that works, you can see that that's what's happening here. We got f of y, cosine and sine, right? But this is the imaginary, right? This is the odd. Oh, well, it's the odd, yeah. So, but odd of y. So anyways, just to put that into perspective, that's what's happening here with the inverse Fourier transform and the forward Fourier transform. And it's also why we need both components. But again, I like to think about it in terms of waves, especially because we're audio programmers, simply because that's what we do, is we program audios with waves, and I feel like it's a little bit more intuitive. Anyway, go check out that video that I made before. Alright, so basically we're just going to implement what we have off of Desmos because we know this formula works. Obviously, if you don't know, this is actually drawing the wave based on the discrete Fourier transform. So, clearly this formula works. So let's go ahead and just implement it inside of here, function DFT. And it's going to take samples, right? Alright, so basically what we're going to do is log the result of the DFT with some samples. So this is going to be an array of real and imaginary values. For now, we'll just do 4. And so basically, let's just go over what we have in Desmos. The Fourier transform is the sum, as you can see, of the cosine and sine Let's just, honestly, we can just copy this code, right? So we can go ahead and, unfortunately I can't really copy from Desmos because I think it uses latex, so that's gonna screw stuff up. So let's just go ahead and go through this. We know that we're getting two components, right? The real and the imaginary. So we'll also be returning an array of a similar fashion with this. So what do we have to do? Well, basically there is an implicit for loop. This is kind of like a for each loop for every point in the sample. So we're going to go ahead and make this for loop. So I'm going to say for, and this is for each bin. So bin is 0. Bin is going to be less than samples.length and bin plus plus. Alright, so now we're going through all that, and we can go ahead and just basically copy this summation. So instead of 1 to z, I'm going to do 0 to z minus 1. So I'm going to call it n though, just n for each sample. So 0. Because again, we're going to go through all the samples, and the DFT is basically a summation of the product of the sample wave at the point and the cosine or sine wave at the point with the given sampling frequency, right? The sampling bin frequency. Alright, so now we have this for loop, and now we can just basically append this value here. So what I'm going to do is go ahead and create an array. So it's going to be called result array, and we're going to say result of bin is also going to be an array. Alright, and so now inside this loop we can go ahead and just let's go ahead and just initialize everything here to 0, 0. That makes the most sense. And then we'll say result bin 0, right, is going to be, because we're summing, we'll do it like this. And it's going to be the value with the sample. So samples at n, right? And keep this in mind, right? This is the real value, so that's going to be 0. Now times the sine value of omega, right? So actually, let's go ahead and to save some computational, or to save some computation, we'll go ahead and just define our frequency as omega. We'll be doing this a couple of times. And this is going to be equal to 2 times math.pi times the bin frequency, right? Now divided by samples.length, right? And then times n, right? Because for this particular bin frequency, right, we're wrapping it 2 pi over the sample length, and then we're multiplying it for each point, right? Each point of the wave, which is why we have times n. Okay, cool. So this is omega, so it's going to be math times sine omega. Or excuse me, I'm on the wrong one. It's math dot cosine. And then it's going to be minus, right? I need to go back to the right one. Yep, minus the imaginary value, which is going to be 1, and then times math dot sine of omega. I'm going to copy this, and we're going to say the imaginary value is is going to be plus or equal to the real component times sine, and then plus, actually, right? And then cosine. So math dot cosine of omega, and it's going to keep doing that, and then at the end we'll just return result. And we do it, and we should get, I believe, there's one thing. By convention, in the discrete Fourier transform, we actually use negative 2 pi. Don't ask me why. I think it simplifies the expansion of it in like matrix form or something, but for coding, it doesn't make a difference, but it does change the numbers a little bit, specifically by negating some of them. So we're going to go ahead and just make this negative for now. And now this is the correct discrete Fourier transform. So that's great, right? But in order for it to be a complete discrete Fourier transform, we need to add an inverse functionality. So we'll add that in, and we'll say false here, and I'll call this DFT1. And we'll log that first. And then we will log the DFT with DFT1 and true. So we do invert it. Alright, so this is a pretty quick check. I'm going to do something. Remember that for the discrete Fourier transform, we go forward with the negative 2 pi, right? But we go backward with the positive 2 pi. And so I'm just going to make a variable called direction that's going to be either negative 1 or 1. It's going to be negative 1 for forwards and 1 for backwards. And so we can do that by just checking if we're doing the inverse. And if so, make this value 1, otherwise negative 1. And we'll just save this here. That'll do that. And as you can see, that it still does what it did before. And then we see a weird issue where we have basically 0, right? And then 4, and then 8, and then 12. So what's going on? Well, these are all multiplied by 4. They're also multiplied by the length. I mean, not both, but they're actually multiplied by the length of the array. So in order to fix that and account for that, only for the inverse, we need to check if we're doing the inverse. And if we are, then we need to divide by the length like we do here. So we'll have to do a for loop. And we'll just have to divide this for both the real and imaginary part. Equal to same here, and not bin, I, and there we go. Just some floating point errors, of course, but as you can see, we get essentially the original array back. We have 0, 1, 2, and 3, which is what we sent in initially, and then our value is basically 0. Those are our imaginary values. And as you can see, our original forward DFT works. So yeah, guys, this is basically how you implement this DFT. It's just basically right off of the Desmos page I have available for you guys. So yeah, it's not too complicated. Again, it's if you watch my other video on the Fourier transform and the discrete Fourier transform, it's pretty straightforward. I mean, this is a pretty straightforward implementation of that. Yeah, that's basically it. See ya.